Imagine staring up at the night sky, where countless stars twinkle like distant lighthouses in an endless ocean of darkness. Now, picture the silence vast, profound, almost deafening. But what if I told you that silence isn't as absolute as it seems? Deep within the cosmic void, hidden beneath the quiet, are whispers, strange, pulsing signals that defy explanation. These aren't the ordinary radio waves or cosmic background noise we've come to expect. They're anomalies, bursts of energy so peculiar that they've left astronomers scratching their heads for decades. Some repeat at intervals so precise they seem almost artificial. Others explode into existence with such intensity that they outshine entire galaxies for mere milliseconds before vanishing without a trace. These are the 25 strange signals from deep space, and they're rewriting everything we thought we knew about the universe. What makes these signals so extraordinary isn't just their mystery, it's what they represent. Each one is a cosmic detective story, a clue waiting to be deciphered. Could they be the echoes of dying stars, the collisions of black holes, or something even more extraordinary? One signal, known as the WOW signal, lasted just 72 seconds in 1977, never to be heard again, yet so powerful it's still debated today. Another, dubbed the Lorimer Burst, arrived with the energy of 500 million suns, only to disappear as quickly as it came. And then there's the chilling possibility that some of these signals might not be natural at all. This isn't just a journey through space, it's a journey through the limits of human understanding. Every strange signal is a question mark hanging in the cosmos, challenging us to look deeper, think bigger, and wonder if we're truly alone. What if one of these signals holds the key to unlocking the universe's greatest secrets, or even proof that we're not the only ones listening? Buckle up, because we're about to dive into the 25 most enigmatic signals ever detected. Each one a story of curiosity, frustration, and the unyielding human drive to uncover the truth. The cosmos is speaking. It's time we learned how to listen. Among all the strange signals ever captured from deep space, none has captured the imagination quite like the WOW signal. Detected on August 15, 1977 by the Big Ear radio telescope at Ohio State University. It lasted for a mere 72 seconds, but in that brief window, it screamed across the cosmos with an intensity unlike anything astronomers had seen before. The signal was so powerful that scientist Jerry Amon circled it on the printout in red pen, writing "WOW" next to it, a name that stuck. What made it extraordinary wasn't just its strength, but its frequency, 1420 MHz, a narrowband radio wave that sits in a protected range of the spectrum where earthly interference is minimal. This was no cosmic static or satellite glitch. It came from somewhere near the constellation Sagittarius, and then it vanished despite 47 years of searching. The WOW signal has never repeated. Theories about its origin range from the plausible to the extraordinary. Some suggest it could have been a comet's hydrogen cloud reflecting sunlight, except none were in the right position at the time. Others argue it might have been a bizarre stellar phenomenon, like a neutron star's magnetic field behaving unpredictably, but the most tantalizing possibility, that it was artificial. The frequency matches what scientists predict an alien civilization might use for interstellar communication, a cosmic hello shouting across the void. Skeptics counter that without repetition, it could just be a freak cosmic event. Yet the signal's precision haunts researchers. If it was natural, why haven't we found anything like it since? If it was artificial, who sent it? The WOW signal is more than just an unsolved mystery. It's a reminder that the universe is vast, unpredictable, and full of surprises. Every attempt to explain it leads to new questions, proving that sometimes the cosmos leaves us with clues that defy easy answers. The WOW signal didn't just vanish into cosmic static. It left an indelible mark on science and culture, reshaping how we search for intelligence beyond Earth. After that fleeting 72-second broadcast in 1977, the search for extraterrestrial intelligence, or SETI, was never the same. Suddenly, the idea of detecting an alien signal went from science fiction to tangible possibility, injecting new urgency into the field. Researchers began designing more sensitive radio telescopes, fine-tuning their equipment to catch these elusive whispers. Projects like SETI Allen Telescope Array, with its 42 dishes scanning the sky simultaneously, owe their existence in part to that single unexplained blip. The WOW signal became the benchmark, the gold standard against which all potential alien transmissions are measured, but its influence stretched far beyond laboratories and observatories. The signal seeped into popular culture, spawning documentaries, books, and even inspiring films like Contact. It turned into a symbol of humanity's cosmic loneliness and our desperate hope that we might not be alone. Every year on August 15th, amateur astronomers and scientists alike commemorate WOW Signal Day, pointing their antennas toward Sagittarius on the off chance it might repeat. The signal even sparked philosophical debates. If we did receive an intentional message, should we reply? Who gets to speak for Earth? These questions forced governments to draft protocols for first contact, outlining how to verify and respond to extraterrestrial signals responsibly. Decades later, the debate over the WOW signal's origin still rages. Mainstream astronomy leans toward natural explanations, like an unusually focused burst of hydrogen emissions from a passing comet or a rare stellar event. But the timing doesn't add up. No known comet was in the right position when the signal arrived. Then there's the unnerving precision. That 1420 MHz frequency sits squarely in the water hole, a quiet band of the radio spectrum between hydrogen and hydroxyl wavelengths that scientists consider ideal for interstellar communication. It's as if someone knew exactly where to shout so we'd hear them clearly. What makes the WOW signal so enduring isn't just its mystery, it's the way it exposes how little we truly understand. For all our technology, one unexplained burst from the void reminds us that the universe still holds cards close to its chest. Whether it was a cosmic coincidence or an interstellar greeting, that 72-second anomaly taught us to listen more carefully to the stars. And as new telescopes come online, capable of scanning millions of frequencies at once, scientists haven't given up hope that one day, another signal will make them circle their printouts in red ink and write, WOW, all over again. While the WOW signal remains a one-time cosmic fluke, some mysterious messages from the deep universe keep coming back, and none are more persistent than FRB 121102. This bizarre burst of radio energy, first detected in 2012, shattered expectations by doing something no other fast radio burst had done before. It repeated. Not just once, but over and over in unpredictable patterns, like a cosmic heartbeat with no rhythm. Most FRBs blast across space in a single, milliseconds-long flash before disappearing forever. But this one, it kept talking. Discovered by the Arecibo Observatory in Puerto Rico, FRB 121102 originates from a dwarf galaxy 3 billion light-years away, a faint, unassuming speck of stars that somehow produces explosions with the energy of 500 million suns. What makes these bursts extraordinary isn't just their power, but their fingerprint. Each pulse is twisted, as if the radio waves have been wrung through a cosmic vortex, suggesting they passed through an incredibly strong magnetic field before reaching us. Astronomers now believe the source sits near a massive black hole or a hypermagnetic neutron star, environments so extreme they warp the very fabric of space-time. The repeating nature of FRB 121102 has allowed scientists to study it in ways impossible with one-off bursts. By tracking its activity, they've noticed something eerie. It follows cycles. For weeks, it might fire off dozens of bursts, then fall silent for months. Some pulses arrive in tight clusters, separated by mere seconds, while others trickle in alone. This unpredictability has fueled wild theories. Could it be an alien beacon, deliberately irregular to avoid appearing natural? More likely, it's a celestial object behaving in ways we've never seen, like a magnetar throwing tantrums or a pulsar caught in a deadly dance with a black hole. Every burst from FRB 121102 carries secrets. In 2017, researchers hit the jackpot. They pinpointed its home galaxy, making it the first FRB with a confirmed cosmic address. That breakthrough revealed another shock. The bursts are erupting from a region brimming with star-forming gas, a nursery for young stars. This contradicts earlier assumptions that FRBs come from elderly, dying stellar systems. Now, some wonder if the source could be a newborn magnetar, a super-dense stellar corpse with a magnetic field 1 trillion times stronger than Earth's, unleashing apocalyptic energy as it settles into existence. The more we learn about FRB 121102, the stranger it gets. In 2020, astronomers detected something unprecedented within its bursts: fine structure, tiny subbursts lasting microseconds like a series of cosmic stutters. This level of detail suggests the bursts might be produced by a mechanism far more intricate than a simple explosion, perhaps plasma jets ricocheting off interstellar debris or shockwaves traveling through a neutron star's magnetosphere. With each discovery, this repeating enigma peels back another layer of the universe's mysteries, proving that sometimes the cosmos doesn't just whisper, it shouts, waits, and shouts again just to make sure we're listening. FRB 121102's repeating bursts have ignited a firestorm of theories among astronomers, each more fascinating than the last. At the heart of the debate lies one leading contender: magnetars. These city-sized corpses of dead stars pack the mass of our sun into a space smaller than Manhattan, spinning with magnetic fields so intense they could strip the iron from your blood from 1,000 light-years away. When these hyper-dense monsters experience starquakes, sudden cracks in their crystalline crusts, they might unleash the colossal energy bursts we detect as FRBs. Recent observations lend weight to this idea. In 2020, astronomers caught our own Milky Way's magnetar SGR 1935+25 firing off an FRB-like pulse, marking the first time we've seen such an event up close. But here's the catch: our homegrown magnetar's burst was thousands of times weaker than FRB 121102's explosions. Could there be supercharged magnetars lurking in distant galaxies, capable of far more violent eruptions? Not everyone is convinced magnetars tell the full story. Another camp points to cosmic collisions, specifically neutron stars smashing into each other or being devoured by black holes. When these incredibly dense objects spiral toward doom, their magnetic fields could twist into braided coils, launching jets of plasma that generate FRBs as they plow through interstellar gas. This might explain FRB 121102's twisted radio waves, but fails to account for its repeating nature. Dead stars typically only collide once. Unless we're witnessing some bizarre cosmic ménage à trois where multiple objects keep interacting across billions of years, this theory leaves gaps. Then there's the elephant in the room: alien technology. While most scientists consider this a remote possibility, the peculiar structure of FRB 121102's pulses keeps the door slightly ajar. Some pulses arrive in mathematically neat intervals, sparking speculation about intentional design. Could these be propulsion signatures from extraterrestrial light sails, using focused energy beams to push spacecraft near light speed? Or perhaps an alien lighthouse deliberately broadcasting in a pattern meant to stand out against natural cosmic noise? Even SETI researchers admit that while improbable, we can't yet rule out artificial origins, especially since the bursts seem to cluster in ways that don't perfectly match known astrophysical processes. The mystery only deepens with recent breakthroughs. In 2022, China's FAST telescope detected over 1,600 bursts from FRB 121102 in just 2 months, a treasure trove revealing new layers of complexity. Hidden within these bursts were distinct echoes, suggesting the signals travel through dense clouds of magnetized plasma near their source. This fits with observations that the burst's polarization changes over time, like a cosmic dial being adjusted. Some researchers now propose the source might be a young, hyperactive magnetar embedded in a nebula of its own making, a stellar toddler throwing radioactive tantrums as it learns to control its incredible power. Yet for every answer, fresh questions emerge. Why do the bursts sometimes arrive in storms of 30 per hour, then vanish for weeks? What causes the microsecond-scale substructures within individual pulses? And most perplexing of all, why is this repeater so utterly alone? Despite discovering over 1,000 FRBs to date, only about 3% repeat, and none behave quite like 121102. It's as if we've stumbled upon a cosmic unicorn, defying every attempt to shove it into existing categories. Whether it's a freak of astrophysics or something even more extraordinary, one thing's certain: this little repeater from a dwarf galaxy 3 billion light-years away continues to rewrite the rulebook on how the universe communicates. Long before scientists discovered repeating FRBs like 121102, there was the Lorimer Burst, the cosmic event that started it all. Back in 2007, radio astronomer Duncan Lorimer and his student David Narkevic were sifting through old data from Australia's Parkes Observatory when they stumbled upon something impossible. A 5-millisecond blast of radio waves so powerful, it packed more energy than our sun emits in 30 days. This wasn't just another blip in the static. It came from 3 billion light-years away, tearing through intergalactic space like a bullet through fog before slamming into Earth's telescopes. And then, just as suddenly as it appeared, it was gone. At first, the scientific community dismissed the finding. The signal was so bizarre that researchers assumed it had to be a glitch, maybe a malfunctioning satellite or some earthly interference. But the numbers didn't lie. The burst's dispersion pattern, how its higher frequencies arrived slightly before the lower ones, revealed it had traveled through an astonishing amount of interstellar plasma, far beyond anything in our galaxy. This wasn't a local phenomenon. It was extragalactic, a scream from another corner of the universe. The discovery upended astronomy's understanding of transient signals. Before the Lorimer Burst, no one imagined such fleeting, energetic events could exist. Now they had proof the cosmos was filled with them, brief, brilliant flashes rewriting the rules of astrophysics in real time. What made this burst so revolutionary was its sheer violence. In those 5 milliseconds, it released as much energy as 500 million suns. Picture a cosmic lightning bolt so intense, it outshone entire galaxies for a fraction of a second. Astronomers scrambled to explain it. Could it be a neutron star collapsing into a black hole, a hypernova's final death throes, or something even more exotic like a theoretical pulsar, a supermassive neutron star delayed from collapsing until its magnetic field finally gave way? The theories flowed, but the burst refused to repeat, leaving scientists with only a single day to point to study. The Lorimer Burst didn't just announce the existence of fast radio bursts, it exposed how blind we'd been to the universe's fleeting wonders. Before 2007, telescopes weren't designed to catch millisecond-scale events. They were built to study steady objects, stars, galaxies, pulsars. This burst forced astronomers to rethink their tools, leading to new wide-field arrays like CHIME in Canada, which now detects dozens of FRBs daily. It also sparked a race to explain their origins, with every new detection adding pieces to the puzzle. Some FRBs we now know come from magnetars, others might involve cosmic collisions, but the Lorimer Burst remains unique, the first glimpse of a phenomenon we're only beginning to understand, a 5-millisecond message from the distant universe that forever changed how we listen to the stars. In the vast cosmic menagerie of strange signals, few have sparked as much controversy or wild speculation as the star known as KIC 8462852 or Tabby's star. Named after astronomer Tabby, who first brought its bizarre behavior to light in 2015, this unassuming star in the constellation Cygnus does something no other star we've observed does. It flickers like a dying light bulb in ways that defy all conventional explanations. Unlike the predictable dips caused by orbiting planets, Tabby's star dims erratically, sometimes by a barely noticeable 1%, other times by a staggering 22%, as if something colossal is passing in front of it. These aren't the clean, symmetrical shadows of planets. They're jagged, asymmetrical, and utterly chaotic. Initial explanations pointed to swarms of comets, hundreds of thousands of them, crumbling as they orbited the star. But even that theory strains credibility. No natural comet family could explain the scale or irregularity of these dips. Then came the hypothesis that set the internet ablaze, the Dyson sphere. Proposed by physicist Freeman Dyson in the 1960s, this theoretical megastructure would be built by an advanced civilization to harness a star's energy, surrounding it with orbiting solar collectors. Could Tabby's star be the first evidence of such a feat? The idea gained traction when astronomers found the star's overall brightness had also been dropping over a century, a trend incompatible with known natural phenomena. Suddenly, the whispers of alien megastructure became impossible to ignore. Skeptics, of course, rushed to offer less sensational explanations. Perhaps the star is surrounded by massive rings of dust warped by an unseen planet's gravity. Or maybe it's consuming a recently captured planetary body, creating irregular debris fields. Even interstellar dust clouds drifting between us and the star could play a role. But each theory comes with holes. Dust, for instance, should scatter infrared light, yet Tabby's star shows no such excess. The lack of a clear answer has turned this distant star into a cosmic Rorschach test, where scientists see what they want to see, proof of alien engineering, or just another puzzle begging for a mundane solution. Recent observations have only deepened the enigma. In 2017, the star dimmed dramatically again, this time allowing telescopes worldwide to capture its behavior in unprecedented detail. The data revealed something unexpected. The dimming wasn't uniform across all light wavelengths. Blue light was blocked more than red, a telltale sign of fine dust particles rather than solid megastructures. This seemed to deal a blow to the Dyson sphere theory, but the mystery wasn't solved. The dust's origin remains unknown, and the century-long dimming trend persists, still lacking a convincing natural explanation. Tabby's star represents something bigger than any single hypothesis. It's a test case for how we confront the unknown. When faced with phenomena that defy our current understanding, do we stretch existing theories to fit, or dare to consider possibilities that challenge the very foundations of science? Whether the culprit turns out to be dust, comets, or something far more extraordinary, this flickering star has already taught us a vital lesson. The universe is stranger than we imagine, and sometimes the most compelling mysteries are the ones that refuse to be solved. The year 2020 delivered what seemed like a breakthrough in the search for alien intelligence, a tantalizing radio signal dubbed BLC-1, emanating from our closest stellar neighbor, Proxima Centauri. Discovered by the Breakthrough Listen project using Australia's Parkes telescope, this narrowband signal at 982 MHz set pulses racing through the scientific community. Unlike the random emissions of natural cosmic phenomena, BLC-1 appeared artificial. It occupied a tight frequency range, drifted in a way that suggested movement relative to Earth, and originated from a star system known to host at least 2 planets, one in the potentially habitable zone. The internet erupted with speculation. Had we finally detected proof of extraterrestrial technology? But science thrives on skepticism, and the initial excitement soon gave way to rigorous scrutiny. The signal's most promising feature, its apparent origin near Proxima Centauri, turned out to be its biggest red flag. Detailed analysis revealed BLC-1 wasn't coming from the star itself, but from a region a few degrees away in the sky. Most damningly, when researchers pointed telescopes back at the same coordinates, the signal had vanished. Further digging uncovered a far more mundane explanation: human-made radio interference, likely from a passing satellite or ground-based electronics. The telltale sign: similar signals began popping up in other datasets, all tracing back to earthly sources. The BLC-1 controversy wasn't just a false alarm, it became a masterclass in how difficult authenticating an alien signal truly is. Modern Earth is awash in radio noise. Satellites, cell towers, microwave ovens, even car engines can produce signals that mimic extraterrestrial transmissions. The Breakthrough Listen team's exhaustive 2-year investigation highlighted the need for multiple verification steps, including simultaneous detection by separate telescopes and ruling out all possible terrestrial sources. Ironically, BLC-1's most suspicious trait, its failure to repeat, was what ultimately downgraded it from potential first contact to footnote. Yet the episode yielded invaluable lessons. It proved our detection methods are sensitive enough to catch extremely faint signals, even if they turn out to be interference. It also forced SETI researchers to refine their protocols, emphasizing the importance of real-time follow-up observations and cross-checking with other instruments. Perhaps most importantly, BLC-1 demonstrated how quickly excitement can outpace evidence when confronting the unknown, a cautionary tale for future detections. As we continue scanning the cosmos, signals like this remind us that extraordinary claims require not just extraordinary evidence, but patience, skepticism, and an unwavering commitment to scientific rigor. The universe isn't making it easy for us to find our cosmic neighbors, but with each false alarm, we're learning to listen more carefully. Of all the signals that have teased scientists with the possibility of extraterrestrial intelligence, few have endured as a tantalizing, maybe quite like SETI-02 plus 14a. Detected in 2003 by the SETI at Home project, a groundbreaking program that allowed millions of home computers to analyze radio telescope data. This faint, fluctuating signal emerged from a patch of sky near the constellation Pisces. What made it stand out wasn't just its artificial-seeming characteristics, but its bizarre location, hovering near a spot where no bright stars, active galaxies, or known cosmic phenomena should be producing such emissions. The signal's most puzzling feature was its frequency, approximately 1420 MHz, the same narrowband range as the WOW signal, nestled in the protected waterhole where cosmic noise is minimal. Even stranger, it appeared to drift, shifting slightly in frequency over time in a way that suggested movement, perhaps originating from a planet orbiting a distant star. But when researchers trained the massive Arecibo telescope on the same coordinates, they found nothing. The signal refused to repeat, leaving astronomers with only 4 faint detections spread across 3 years, each too weak to confirm definitively. Adding to the enigma, the signal's apparent source region contained only one notable object, a white dwarf star, the cooling corpse of a sun-like star long past its prime. White dwarfs are stellar gravestones, slowly fading into darkness over billions of years, hardly the type of object expected to host intelligent life. Yet the signal's frequency and drift kept the door slightly ajar. Could it be an alien transmitter orbiting this dead star, harnessing its residual heat, or perhaps a beacon placed deliberately near such an inconspicuous object to avoid detection? Skeptics argue the signal was likely interference from earthly sources, amplified by the SETI at Home system's distributed processing, like a cosmic game of telephone where noise gets mistaken for signal. The truth may never be known. Without repetition, SETI-02 plus 14 remains frozen in scientific limbo, too intriguing to dismiss entirely, too elusive to prove. Yet its legacy endures. It demonstrated the power of citizen science, proving that millions of volunteers could contribute to the search for extraterrestrial intelligence. It also exposed the needle in a haystack challenge of SETI. even when you find a needle, how do you know it's not just a stray piece of straw? For now, this ghostly signal lingers as a reminder that the universe rarely serves up answers without a fight, and that even a dead star's neighborhood might hold secrets we've only begun to imagine. In 2015, a star 194 light-years away sent astronomers into a frenzy with a signal that seemed too perfect to ignore. HD 164595, a sun-like star in the constellation Hercules, suddenly became the center of attention when Russian astronomers detected a powerful radio burst at 11 GHz, a frequency with no known natural explanation. What made this pulse electrifying wasn't just its intensity, but its duration, a full 2 seconds, far longer than the millisecond bursts typically emitted by cosmic phenomena. Even more intriguing, the star hosts at least one Neptune-sized planet, raising the tantalizing possibility of a civilization advanced enough to broadcast across the cosmos. Initial calculations suggested the signal would have required immense energy to reach Earth, equivalent to harnessing the entire output of a star like our Sun. If artificial, this wasn't some accidental leakage like our own radio and TV broadcasts. This would be a deliberate, focused transmission, a cosmic spotlight aimed squarely in our direction. The discovery quickly reached SETI scientists, who scrambled to train the Allen telescope array on HD 164595, hoping to catch a repeat. Excitement built as speculation swirled. Had we stumbled upon a hello from a type Roman II civilization, one capable of harnessing their star's total energy? But the euphoria was short-lived. Within weeks, skeptics identified glaring issues. The signal's frequency, while unusual for natural astrophysical processes, sits squarely in the band used by military and communication satellites. More damningly, when other telescopes tried to verify the detection, they found nothing, not even a whisper. The signal's one-time appearance and lack of repetition pointed toward earthly interference, perhaps a passing satellite or radar burst reflected off space debris. Even the original Russian team admitted their data had inconsistencies, with the signal appearing in only one of their 2 receiver systems. The HD 164595 episode became a cautionary tale about the perils of jumping to cosmic conclusions. Yet buried beneath the disappointment lies an important truth. Our detection methods are improving. This false alarm proved we can now identify fleeting, narrowband signals across vast distances, a capability that would have been unimaginable decades ago. While the star remains silent, its brief moment in the spotlight reminds us that the line between groundbreaking discovery and mundane interference is often razor-thin. Every dead end teaches us to listen more carefully, filter more precisely, and wait more patiently, because somewhere out there a real signal might be waiting, one that won't fade away when we double-check. In the quiet pre-dawn hours of November 28, 1967, Cambridge astrophysicist Jocelyn Bell Burnell was reviewing data from her radio telescope when she stumbled upon something extraordinary. A series of pulses arriving every 1.337 seconds with atomic clock precision. The signal, coming from a patch of sky near Vulpecula constellation, was unlike anything natural science had documented. So unnervingly regular were these pulses that Burnell and her supervisor Anthony Hewish jokingly labeled them LGM-1, short for Little Green Men. The implication was clear. They were staring at what might be the first confirmed transmission from an extraterrestrial civilization. What made these pulses so unsettling was their artificial-seeming rhythm. Unlike the chaotic emissions of stars or galaxies, these ticks arrived with metronomic consistency, like a cosmic drumbeat counting down to first contact. The pulse's narrow frequency range further heightened the mystery, mimicking what scientists predicted an interstellar beacon might look like. For weeks, the Cambridge team operated under hushed secrecy, terrified their discovery might trigger global panic if leaked prematurely. They quietly nicknamed 3 additional sources LGM-2 through 4, imagining an intergalactic network of alien outposts signaling across the void. The truth, when it came, was both more mundane and infinitely stranger. These weren't alien broadcasts, but the birth cries of a previously unknown celestial object, the pulsar. These rapidly spinning neutron stars, the dense corpses of supernova explosions, beam radiation from their magnetic poles like cosmic lighthouses. As they rotate, their beams sweep across Earth at predictable intervals, creating the illusion of deliberate signaling. The first confirmed pulsar, later named CP19-1921, was clocking 642 revolutions per second, its precision rivaling atomic timekeepers. The LGM episode wasn't just a false alarm, it rewrote astrophysics textbooks. Pulsars became nature's ultimate cosmic clocks, helping test Einstein's theory of relativity with unprecedented precision. Their discovery also taught astronomers a humbling lesson. The universe often imitates art. The same characteristics that make pulsars invaluable to science, their regularity, their narrowband emissions, are precisely what SETI researchers look for in artificial signals. This creates an ongoing challenge: how to distinguish between nature's ingenious mimics and the real deal. Modern pulsar research continues to blur this line. Some pulsars, like PSRB 1257+12, have such perfectly timed pulses that they initially appear to carry encoded messages. Others exhibit glitches or sudden speed-ups in rotation that briefly make their signals resemble the erratic patterns we might expect from malfunctioning alien technology. The most bizarre, PSRJ 1906+0746, emits pulses that occasionally vanish for minutes before restarting, as if someone keeps flipping a cosmic switch. The legacy of the LGM pulsar endures as a reminder that nature often outstrips our imagination. What began as a potential first contact scenario revealed instead a new class of celestial phenomena, one that continues to challenge our assumptions about where to draw the line between the natural and the artificial. Every time a new pulsar is discovered, astronomers must ask themselves, is this another cosmic timekeeper, or could it finally be the real LGM we've been waiting for? The answer, as Bell Burnell learned, might surprise us all. For years, astronomers hunting for fast radio bursts stumbled upon a baffling phenomenon: signals that looked almost identical to FRBs, but with one glaring difference. These mimics, nicknamed Puritans, arrived during daylight hours exclusively at Australia's Parkes Observatory, seeming to originate not from distant galaxies but eerily close to Earth. Unlike genuine FRBs, whose dispersion suggested they'd traversed intergalactic space, Puritans showed barely any dispersion at all, as if they'd traveled only a few hundred miles. The mystery deepened when researchers noticed these signals clustered around local lunchtimes, sparking wild theories: secret military experiments, atmospheric anomalies, or even bleeding-edge technology leaking strange emissions. The breakthrough came thanks to an observatory staff member's keen observation. One day, as a Puritan detection lit up their equipment, someone happened to open a microwave oven door mid-cycle. The timing was uncanny. A quick test confirmed it. When opened prematurely, the observatory's microwave emitted a burst of radio waves nearly identical to the perplexing signals. The culprit wasn't extraterrestrial, it was a hungry astronomer reheating leftovers. The magnetron inside the microwave, interrupted mid-operation, produced a frequency-swept pulse that the sensitive radio telescope mistook for a cosmic event. Even the lunchtime pattern made sudden sense. These were moments when staff typically fetched meals. What makes the Puritan saga more than just a humorous blunder is how it exposed a critical blind spot in astrophysics. For years, researchers had dismissed the idea that terrestrial interference could mimic FRBs so precisely. The signal's frequency sweep, caused by the microwave's magnetron discharging as the door opened, was virtually indistinguishable from the dispersion effects of genuine FRBs passing through interstellar plasma. This revelation forced astronomers to overhaul their verification protocols. Now, observatories rigorously screen for local interference, monitoring everything from Wi-Fi routers to aircraft radar. The Puritan episode became a textbook case of how human activity can masquerade as cosmic phenomena, reminding scientists that sometimes the most alien-looking mysteries are hiding in plain sight right in the break room. In the summer of 2017, astronomers at Puerto Rico's Arecibo Observatory turned their massive dish toward Ross 128, a quiet red dwarf star just 11 light-years away. What they found would send ripples through the scientific community, a bizarre 10-minute radio burst that defied easy explanation. Unlike the chaotic emissions of typical stellar flares, this signal appeared narrowband, centered around 5 GHz, with a drifting frequency pattern that mimicked what scientists might expect from a transmitter on a rotating planet. Here was a star with 3 known rocky worlds, one potentially in the habitable zone, suddenly broadcasting a signal that checked multiple boxes for artificial origin. The mystery deepened when researchers noticed something peculiar. The signal only appeared when observing Ross 128, vanishing when the telescope pointed elsewhere. This ruled out most terrestrial interference, which would have affected multiple targets. Yet the signal's characteristics didn't quite match known stellar activity either. Red dwarfs like Ross 128 are notorious for violent flares, eruptions of plasma that can bathe orbiting planets in deadly radiation. But those flares typically emit across wide frequency ranges, not in the tight, almost laser-like band observed. Some team members even noted the signal's structure had an uncanny resemblance to human-made satellite transmissions, though no known satellites operated at that frequency near Ross 128's position. Alternative explanations quickly emerged. Could the signal be a side effect of solar activity reflecting off passing space debris, or perhaps an undocumented quirk of the telescope itself? The most plausible natural theory involved an unusual type of stellar flare, one where plasma conditions in the star's atmosphere amplified specific frequencies, creating a false narrowband appearance. Supporting this, Ross 128 belongs to a class of stars prone to superflares, events thousands of times more energetic than anything our Sun produces. If one of these eruptions occurred along our line of sight, its interaction with the star's magnetic field might have produced the illusion of a structured signal. What makes the Ross 128 anomaly so compelling isn't just its unresolved nature, it's the star itself. Red dwarfs outnumber all other stars combined in our galaxy, and their longevity means they could host civilizations far older than ours. A signal from such a nearby system, even if likely natural, forces us to confront how little we understand about stellar behavior. Follow-up observations have yet to detect a repeat, leaving astronomers divided. Some dismiss it as a quirky flare, while others quietly wonder if we caught a fleeting glimpse of something more deliberate, a cosmic hello from a star system practically next door. Until Ross 128 speaks again, its mysterious transmission remains a haunting reminder that sometimes the universe winks at us just long enough to make us question everything we think we know. While fast radio bursts dazzle with their millisecond brilliance, another cosmic phenomenon burns even brighter and weirder. Meet the fast blue optical transient, or FBOT, a flare so intense it can outshine entire galaxies for weeks before vanishing without a trace. Unlike anything seen before, these eruptions blast blue light across the universe with the energy of 1,000 supernovae, leaving astrophysicists scrambling for explanations. First discovered in 2018, FBOT challenge everything we know about stellar explosions. Supernova unfold over months, their light curves following predictable patterns as they expand. FRBs last mere milliseconds, their radio waves flickering like cosmic Morse code. But FBOT, they're the universe's flashbulbs, ultra-bright, ultra-rare, and ultra-mysterious. Take a 2018 COW, the most famous example. Detected in a galaxy 200 million light-years away, it flared to peak brightness in just 2 days, 10 times faster than a typical supernova, then faded into obscurity within a month. Its blue hue hinted at temperatures exceeding 20,000 degrees Celsius, hotter than most known stellar remnants. The leading theories range from the catastrophic to the outright bizarre. Some suggest F-bot are failed supernova stars that collapsed into black holes so abruptly, their outer layers bounced off the newborn singularity in a shockwave of light. Others propose they're tidal disruption events on steroids, where a star isn't just torn apart by a black hole, but violently compressed into a jet of plasma moving near light speed. Then there's the wild card magnetar formation. If a newborn magnetar's magnetic field spins fast enough, it might convert that energy into an F-bot dazzling light show. What sets these events apart isn't just their violence, it's their structure. Analysis of a 2018 COW revealed expanding debris moving at 1/10 light speed, yet the light curve didn't match any known explosive model. Spectroscopy uncovered another puzzle, heavy elements like calcium and titanium glowing fiercely, as if the explosion had dredged up material from the star's deepest layers. This suggests F-bot aren't just surface-level eruptions, but deep cosmic excavations, uncovering stellar secrets we've never witnessed before. The hunt for answers is complicated by F-bot's elusiveness. Only a handful have ever been detected, each one slightly different. Some, like ZTF-20 SLA, flare and fade symmetrically. Others, like CSS 161010, flicker erratically like a candle in cosmic wind. This variation implies multiple mechanisms might be at play, perhaps a cosmic zoo of explosions we're only beginning to catalogue. Unlike FRBs, whose repeating patterns offer clues, F-bot are one-shot mysteries. Once they fade, they're gone forever, taking their secrets with them. Yet every new detection peels back another layer of their strangeness, proving that even in a universe filled with flashes and bangs, some explosions still defy explanation. Whether they're stellar death throes, black hole tantrums, or something even more exotic, F-bot remind us that the cosmos keeps its most spectacular fireworks hidden until suddenly, brilliantly, it doesn't. Beneath the familiar cosmic microwave background, the afterglow of the Big Bang itself lurks something unsettling. Astronomers call it dark flow, a peculiar drift in the motion of galaxy clusters that defies everything we know about cosmic expansion. Imagine throwing confetti into the air, only to watch every piece inexplicably drift toward one corner of the room. That's the essence of dark flow, thousands of galaxy clusters, each containing trillions of stars, all streaming in the same direction at nearly 2 million miles per hour. The kicker, there's nothing out there massive enough to pull them. This wasn't supposed to happen. According to standard cosmology, the universe expands evenly in all directions, with matter distributed uniformly enough that no single region should exert such overwhelming gravitational influence. Yet data from NAS, a Wilkinson microwave anisotropy probe, and the Planck satellite confirmed the anomaly galaxy clusters moving en masse toward a patch of sky between the constellations Centaurus and Vela. The force required to tug them would dwarf the combined mass of every known galaxy. So what's doing the pulling? One radical possibility, a neighboring universe. Some theorists suggest dark flow could be the gravitational imprint of a parallel cosmos beyond our observable horizon, its mass warping our space-time like a magnet tugging on iron filings. In this scenario, our universe isn't alone but one bubble in an infinite multiverse, with other bubble universes floating close enough to exert tidal forces. The idea remains speculative, but it's mathematically plausible, and would explain why the flow's source appears to lie beyond the edge of everything we can see. Skeptics propose less exotic explanations. Maybe incomplete data or measurement errors created the illusion of motion. Others argue peculiarities in the cosmic microwave background, like temperature asymmetries, could generate false flow signals. But each time researchers account for one variable, dark flow persists. Even accounting for known superclusters, the motion remains unexplained, as if the universe is whispering that our inventory of matter is woefully incomplete. The implications are staggering. If dark flow stems from unseen mass, it hints at structures beyond comprehension, perhaps vast sheets of dark matter or concentrations of energy left over from the Big Bang's first moments. If it's evidence of a parallel universe, it rewrites our understanding of reality itself. For now, the phenomenon remains one of cosmology's deepest puzzles, a reminder that even the oldest light in the universe still carries secrets waiting to be decoded. Every time we map the cosmic microwave background, we're not just studying the past, we might be glimpsing the contours of realities beyond our own. In 2008, astronomers tracking the spiral arms of NGC 6946, the so-called fireworks galaxy for its frequent supernova, caught something utterly unexpected. Amidst the usual stellar explosions, a brilliant X-ray flare erupted without warning, blazing with the intensity of 10 million suns before vanishing just days later. This wasn't a supernova, it wasn't a gamma-ray burst, it was a cosmic hiccup, a blip so strange that researchers coined a new term for it, the X-ray blip, a transient event defying every known stellar playbook. The flare originated near the galaxy's star-dense core, where massive stars live fast and die violently. At first glance, it resembled a typical black hole snack, a star torn apart by tidal forces. But the timeline didn't fit. Tidal disruption events unfold over months, their X-rays fading gradually as stellar debris spirals into oblivion. This flare, it skyrocketed to peak brightness in under 48 hours, then disappeared within a week, leaving behind no visible remnant, no expanding shockwave, not even a wisp of infrared afterglow. It was as if the universe had flipped a switch, on, then off, with no explanation. Theories swirled like cosmic debris. One camp proposed a failed supernova, a star massive enough to collapse directly into a black hole without the usual fireworks. In this scenario, the outer layers might plummet inward so abruptly that they'd ricochet off the newborn singularity, creating a brief X-ray scream before vanishing into darkness. Supporting this, the fireworks galaxy is a notorious stellar graveyard, with 6 supernovae observed in just the past century alone. If any place could breed such exotic deaths, it's here. Others pointed to pulsar glitches, sudden speed-ups in a neutron star's rotation. When these ultra-dense stellar corpses stumble, their magnetic fields can unleash torrents of X-rays. But even the most extreme glitches couldn't account for the blip's sheer luminosity. Then came the dark horse theory, a black hole's last meal. Some models suggest intermediate mass black holes, lurking between stellar and supermassive classes, might gulp down dense clusters of white dwarfs or neutron stars in one sitting, producing short, intense X-ray bursts. What makes this blip so tantalizing is what happened next: nothing. Despite years of monitoring, NGC 6946 has never repeated the performance. No follow-up flare, no fading echo, just silence. This absence of evidence is in its own way evidence of something extraordinary. Most cosmic explosions leave forensic traces, expanding shells of gas, heated dust, or lingering radio emissions. The X-ray blip left nothing but questions, a ghostly fingerprint on the universe's window. Perhaps the most unsettling possibility is that we witnessed a cosmic rarity, an event so fleeting that catching it once was pure luck. Like stumbling upon a lightning strike in a desert, the blip might represent a phenomenon occurring across the universe but vanishing before our telescopes can pivot. Future observatories like the European Space Agency's Athena X-ray telescope could finally crack the code if another blip dares to flicker. Until then, this enigmatic flare remains a celestial whisper, reminding us that even the most violent galaxies still harbor secrets waiting to scream. Hidden among the catalogue of cosmic radio bursts lies a peculiar subset that refuses to fit the usual patterns, the DT signals, short for dispersion inconsistent transient incidents. These bursts arrive with a telltale anomaly. Their radio waves don't disperse the way physics says they should. Normally, as radio signals travel through interstellar space, higher frequencies outpace lower ones, creating a predictable smear across the spectrum. But DT bursts, they break the rules, arriving with dispersion measures so inconsistent they've left astrophysicists debating whether they've stumbled upon a new cosmic phenomenon, or something far more unsettling. The first confirmed DT burst appeared in 2019, buried in data from the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Unlike typical fast radio bursts which show smooth dispersion curves, this signal's frequencies arrived scrambled, as if parts of the transmission had taken different routes through space. At first, researchers assumed equipment error, perhaps a glitch in CHIME processing software. Then came a second burst, then a third, all exhibiting the same bizarre trait. The most compelling example, DT7, originated from a galaxy 2.5 billion light-years away, yet its dispersion pattern suggested it had traversed far less plasma than expected, like a radio signal slipping through hidden cosmic shortcuts. Natural explanations abound, though each comes with caveats. One theory posits that DT bursts pass through exotic plasma clouds, regions where magnetic fields twist so violently they alter dispersion in unpredictable ways. Another suggests they're produced by cosmic lighthouses, rapidly spinning neutron stars whose beams intersect dense pockets of interstellar material, warping the signal's journey. The most tantalizing natural hypothesis involves primordial black holes. If these ancient, minuscule black holes exist in abundance, their gravitational lenses might briefly focus certain frequencies, creating the illusion of inconsistent dispersion. Yet there's an elephant in the room, the possibility that these bursts aren't natural at all. SETI researchers note that intentional signals could mimic DT characteristics. An advanced civilization might employ dispersion masking, deliberately structuring transmissions to appear scrambled, ensuring only recipients with the right decoding technology could reassemble the message. The inconsistent dispersion could even be a beacon's calling card, a way to shout, "We're here," amid the cosmic noise without revealing content prematurely. This wouldn't be unprecedented. During the Cold War, militaries used similar frequency hopping techniques to avoid jamming. The debate took a provocative turn in 2021 when two DT bursts exhibited another oddity. They repeated but not identically. Each recurrence showed slight variations in dispersion, as if the source were adjusting its transmission parameters. Natural phenomena rarely fine-tune their behavior so precisely, whereas technological signals often iterate for efficiency. Skeptics counter that magnetars, highly magnetic neutron stars, can exhibit complex rotational behaviors that might produce similar effects. But with no known magnetar matching DT burst locations, the argument remains speculative. What makes these signals so compelling is their defiance. They don't just challenge our understanding of radio propagation, they taunt it, waving inconsistencies like red flags in a cosmic game of Clue. Whether they're plasma-warped screams from dying stars or encrypted greetings from distant minds, one thing's certain: the universe keeps inventing new ways to surprise us. Every DT burst is a reminder that for all our telescopes and algorithms, deep space still holds puzzles we're only beginning to articulate, let alone solve. Just 1,200 light-years away, practically our cosmic backyard, the Geminga pulsar broadcasts eerie gamma-ray pulses that have baffled astronomers for decades. Discovered in 1972 by NASA SAS-2 satellite, this dense neutron star should by all rights behave like every other pulsar, spinning rhythmically, its beams sweeping past Earth with metronomic precision. But Geminga doesn't play by the rules. Instead of the steady tick-tock of radio pulses we expect, it unleashes gamma rays in erratic bursts, flickering like a candle in cosmic wind, as if something inside this stellar corpse is fundamentally broken. What makes Geminga truly bizarre isn't just its refusal to pulse predictably, it's the sheer intensity of its gamma-ray emissions. Most pulsars shine brightest in radio waves, their beams powered by magnetic fields funneling particles outward. Geminga, it's nearly radio silent, channeling almost all its energy into gamma rays, the universe's most energetic light. It's as if someone replaced a lighthouse's gentle beam with a strobe light from the depths of hell. Even stranger, those gamma rays arrive in clusters, sometimes stacking multiple pulses atop one another, other times vanishing for hours. The only other celestial object that behaves this way is the famous crab pulsar, except Geminga is older, colder, and shouldn't have enough energy left to produce such fireworks. The leading theory involves Geminga's peculiar environment. Unlike most pulsars, which scream their presence across radio frequencies, this one orbits through a dense cloud of its own making, a nebula of charged particles trapped in its magnetic field. As the pulsar spins, its magnetic field lines twist and snap, accelerating particles to near light speed. These particles then slam into the surrounding nebula, generating gamma rays in chaotic splashes rather than clean pulses. Think of it like a car engine misfiring. Instead of a smooth hum, you get unpredictable sputters and surges as fuel burns unevenly, but there's a wrinkle. Observations from NASA's Fermi Gamma Ray Space Telescope revealed something unsettling. Geminga's gamma ray pulses aren't just random. They follow a hidden rhythm, with subtle delays between clusters that suggest something deep inside the neutron star is modulating the outburst. Some researchers speculate that Geminga might have a fractured crust, its surface cracked like an eggshell by intense magnetic stresses. As the star spins, these cracks open and close, briefly exposing superheated interiors that vent gamma rays in erratic geysers. Others propose the pulses are influenced by an unseen companion, a rogue planet or dark matter clump, whose gravity tugs on Geminga's magnetic field like a child yanking a jump rope. The most tantalizing clue came in 2021 when astronomers detected gamma-ray echoes around Geminga, faint, delayed pulses that arrived milliseconds after the main burst. These echoes imply the gamma rays are ricocheting off structures near the pulsar, perhaps debris from a long-dead companion star or even a disk of material Geminga hasn't fully evaporated. If confirmed, it would mean this neutron star isn't just a lone wanderer but a cosmic cannibal still digesting its past. Geminga's defiance forces us to rethink how neutron stars age. Conventional wisdom says pulsars slow down, cool off, and fade into obscurity as their magnetic fields decay. Yet here's Geminga, a supposed stellar corpse pumping out gamma rays with the vigor of a much younger object. Its very existence hints that neutron stars might have second acts, hidden reservoirs of energy that ignite long after their birth screams fade. Every erratic pulse is a reminder that even the most well-studied corners of the cosmos can still surprise us, whispering secrets in a language of light we're only beginning to decode. Just when astronomers thought they'd seen the strangest of Tabby's star's antics, the cosmic enigma doubled down. Years after its initial discovery, the star once again grabbed headlines with a fresh series of dimming events, each one deeper and more inexplicable than the last. In 2017, the star plunged into its most dramatic fade yet, losing 22% of its brightness over just a few days, a fluctuation that defied all known stellar behavior. Telescopes around the world swiveled to watch, capturing data in real time as the star flickered like a candle in a draft. But this wasn't a one-time fluke. Over the next 3 years, Tabby's star staged multiple encores, dimming erratically by 5% here, 15% there, as if something vast and unseen were drifting across its face in uneven, jagged motions. The new observations only deepened the mystery. Unlike the smooth, symmetrical dips caused by planets, these events showed bizarre asymmetry-like curves with steep drop-offs and gradual recoveries, or sudden brightening midway through a dimming event. One particularly strange episode in 2019 featured a stair-step pattern where the star's light dropped in distinct phases rather than a single smooth decline. This wasn't the behavior of comets or planets. It looked almost mechanical. Scientists scrambled to explain the madness. The comet swarm theory, once a leading contender, began crumbling under scrutiny. For comets to produce such deep, irregular dips, they'd need to be improbably massive, thousands of times larger than anything in our solar system, and clustered so densely they'd collide and vaporize within centuries. Dust clouds from colliding planets possible, but the star's infrared emissions didn't match the telltale warmth of fresh debris. Then came a radical new idea, a colossal, misshapen dust ring, warped by the gravitational tug of an unseen planet. Computer simulations showed how a giant exoplanet with a tilted orbit could distort its surrounding dust into a lopsided, clumpy structure, one that might explain the star's erratic flickering. Yet even this theory couldn't account for everything. The star's century-long dimming trend, first noted in 2016, remained stubbornly unexplained. No known dust configuration persists for that long without dispersing or replenishing. Some researchers floated the idea of a dusty dwarf star passing through Tabby's system, dragging a millennia-long tail of debris. Others pointed to stellar magnetism, suggesting the star itself might be undergoing strange internal convulsions that alter its brightness. Amid the fray, the Dyson sphere hypothesis refused to die quietly. While most astronomers dismissed it, a stubborn minority noted that an incomplete Dyson swarm, a patchwork of orbiting solar collectors, could produce irregular dips as its segments drifted in and out of alignment. The 2017 event's wavelength-dependent dimming, where blue light faded more than red, initially seemed to rule out solid megastructures, but newer models showed how advanced civilizations might use materials that preferentially scatter shorter wavelengths, mimicking dust's effects. The debate reached a fever pitch in 2021 when Tabby's star did something unprecedented. It dimmed and brightened simultaneously at different wavelengths. While optical telescopes recorded a 4% fade, ultraviolet instruments detected a 12% surge, a reverse shadow that left researchers speechless. Natural explanations struggled to reconcile the data. Dust doesn't behave that way, neither do comets, planets, or stellar flares. The observation was so peculiar that even SETI researchers quietly reinvigorated their scans of the system, searching for any hint of structured signals beneath the chaos. Today, Tabby's star stands as a testament to cosmic humility. With each new observation, it offers not answers but deeper questions. Whether the culprit is dust, magnetism, or something beyond our current understanding, one thing is clear: this star isn't done surprising us. Every flicker, every bizarre light curve, is a reminder that the universe reserves its strangest behaviors for those willing to look and keep looking when others might turn away. In October 2017, astronomers spotted something unprecedented hurtling through our solar system, a dark, reddish object moving too fast to be bound by the sun's gravity. Named Oumuamua, Hawaiian for scout, this interstellar visitor became an instant sensation, not just for its origin beyond our star system, but for how bizarrely it behaved. The first red flag, its shape. While most asteroids and comets are roughly spherical or lumpy, Oumuamua appeared cigar-shaped, at least 10 times longer than it was wide, an architecture never before seen in natural space debris. Then came the real shocker. As it departed, Oumuamua accelerated unpredictably, as if propelled by some unseen force. At first, scientists assumed outgassing, the venting of gases heated by the sun, which can give comets a gentle push. But Oumuamua showed no visible coma or tail, the classic hallmarks of outgassing. The acceleration was too strong, too smooth, as if something were nudging it along. This oddity sparked a firestorm of debate. Harvard astrophysicist Avi Loeb famously floated the idea that Oumuamua might be artificial, a light sail or derelict spacecraft from another civilization drifting between the stars. The hypothesis wasn't entirely fringe. The object's unusual reflectivity and motion matched predictions for how a thin, pancake-like solar sail might behave. Yet nature, as always, had alternative explanations. Some researchers proposed that Oumuamua was a cosmic dust bunny, a fragile aggregate of interstellar material that could vent hidden hydrogen reserves as it warmed, explaining the acceleration without visible outgassing. Others suggested it might be a chunk of nitrogen ice carved from an exo-Pluto, slowly sublimating in sunlight. The most compelling natural theory: Oumuamua was a remnant of a shredded planet, a shard of rock ejected during some cataclysmic event in its home system, tumbling through space with odd rotation and texture. The debate crystallizes a fundamental tension in astronomy. When does weird become alien? Oumuamua's true nature may never be known. It's now beyond the reach of our telescopes, a fleeting enigma swallowed by the void. But its legacy endures, challenging us to refine how we study interstellar objects. Future visitors, like the similarly strange comet Borisov in 2019, will be scrutinized with even sharper eyes. Whether Oumuamua was a bizarre cosmic fluke or something more extraordinary, its passage taught us one vital lesson. The universe doesn't just send us messages sometimes, it sends messengers. And not all of them play by the rules we know. Back in 2010, astronomers made an announcement that sent shockwaves through the scientific community. They discovered Gliese 581g, an exoplanet orbiting snugly within its star's habitable zone where liquid water could theoretically exist. But what turned heads even more was a subsequent claim by astronomer Ragbir Bathel, who reported detecting a strange, laser-like pulse from the same region of space years earlier. Suddenly, this distant world wasn't just another exoplanet. It became the centerpiece of a fiery debate about whether we'd stumbled upon evidence of alien technology. Gliese 581g's credentials were tantalizing. Orbiting a red dwarf star just 20 light-years away, the planet was roughly 3 times Earth's mass, with surface gravity that might allow for a stable atmosphere. Initial models suggested it could be tidally locked, one side permanently facing its dim sun while the other languished in eternal night. Yet even with these extremes, theorists speculated that a twilight band along the Terminator line might offer temperate conditions perfect for life. Then came Bathel's bombshell, his unverified detection of a sharp, artificial-looking light spike in 2008, years before the planet's official discovery. The pulse was brief but intense, matching predictions for how an advanced civilization might use targeted lasers for communication. Skeptics pounced immediately. The signal was never independently verified, and no follow-up observations ever replicated it. Even the planet's existence came under fire. Subsequent studies by other teams failed to confirm Gliese 581g in their data, suggesting it might be a false positive caused by stellar activity masquerading as a planetary signature. Red dwarfs like Gliese 581 are notoriously volatile, prone to flares that can mimic the gravitational tug of orbiting worlds. The European Southern Observatory's HARPS instrument, which initially identified the planet, later revised its findings, conceding the signal might just be noise in the data. Yet the controversy refused to die. Supporters of the original detection argued that the planet's orbit, an eccentric path that would periodically bring it deeper into the habitable zone, made it uniquely interesting. They pointed to the star's other confirmed planets, including Gliese 581d, another promising candidate for habitability. If life existed in that system, they reasoned, why couldn't it evolve to harness laser communication? The debate took a philosophical turn when NASA David Grinspoon noted that dismissing potential technosignatures outright risks a dangerous bias in the search for extraterrestrial intelligence, what he called the giggles factor, where scientists avoid even investigating anomalies for fear of ridicule. Today, Gliese 581G remains in limbo, neither confirmed nor fully debunked. But its legacy endures as a case study in how emotion and science collide when confronting the unknown. For a brief moment, this unassuming exoplanet became a mirror, reflecting our deepest hopes and fears about what or who might be out there. Whether it was ever real hardly matters now. What lingers is the lesson. In the search for cosmic company, sometimes the loudest signals aren't the ones from space, but the debates they ignite here on Earth. On the morning of June 30th, 1908, a blinding fireball tore through the skies above Siberia, leveling 800 square miles of forest near the Tunguska River in an explosion 1,000 times more powerful than Hiroshima. For over a century, the event has remained one of Earth's greatest cosmic mysteries. No crater, no fragments, just 80 million trees flattened in a radial pattern, as if swatted by an invisible giant. But decades after the blast, something even stranger emerged. Radio operators worldwide reported eerie echoes lingering in the atmosphere for days, as if the very fabric of space had briefly rippled with an otherworldly signal. Some researchers propose these weren't just atmospheric disturbances, but evidence of something far more exotic, an antimatter meteorite annihilating itself upon impact. When matter and antimatter collide, they convert entirely into energy, potentially explaining the absence of debris. Theoretically, such an event could also produce a burst of high-frequency radio waves as the annihilation ripples through Earth's magnetic field. Supporting this, witnesses describe the Tunguska blast as unusually bright, with a peculiar bluish light inconsistent with typical meteor strikes. Even stranger, barometric records from that day show a pressure wave that circled the globe twice, something only thermonuclear explosions or massive asteroid impacts typically produce, yet seismic stations detected no telltale vibrations of a solid object hitting the ground. Another fringe theory suggests the explosion wasn't a meteor at all, but a catastrophic failure of an alien spacecraft's propulsion system, a notion fueled by reports of cylindrical or pipe-like objects seen in the sky before the blast. Proponents point to the peculiar way trees fell in a butterfly-shaped pattern, consistent with an aerial explosion splitting into two fireballs before impact. If a vessel using advanced technology, perhaps a matter-antimatter drive, suffered a critical malfunction, the resulting energy release could match the observed devastation while leaving no conventional remnants. Soviet scientists in the 1960s even claimed to find metallic fragments with unusual isotopic ratios in the soil, though these findings remain controversial. The most haunting possibility: Tunguska wasn't an isolated incident but a cosmic message or warning. In the 1970s, radio astronomers noted that the explosion's timing coincided with Earth passing through the Beta Taurid meteor stream, a debris field from Comet Encke. Some theorize this stream contains dense pockets of exotic matter or dormant alien probes, periodically interacting with our planet. If true, the radio echoes might not have been random noise but the remnants of a triggered signal, like a tripwire alerting something or someone to our presence. Whether a freak antimatter collision, a dying spacecraft, or something beyond our comprehension, Tunguska's echoes continue to resonate through science. Each new theory forces us to confront how little we understand about the universe's capacity for violence, and how easily the line between natural catastrophe and cosmic intrigue can blur. The trees still lie where they fell, a silent testament to the day the sky roared, and the stars perhaps answered back. For decades, conspiracy theories have swirled around an alleged ancient alien satellite nicknamed the Black Knight, said to be orbiting Earth for 13,000 years. Stories claim it transmits mysterious radio signals, shows up on NASA feeds, and even predates human spaceflight. Fueling speculation, it's an extraterrestrial artifact monitoring our planet. But peel back the layers, and you'll find a fascinating collision of misinterpreted science, real space oddities, and the human tendency to see patterns where none exist. The myth took root in 1954 when newspapers reported that Air Force officials had detected two mysterious satellites orbiting Earth, impossible at the time, since Sputnik wouldn't launch for another 3 years. The story was later debunked as misidentified natural phenomena, but the legend snowballed. By the 1960s, amateur radio operators claimed to intercept coded signals from the black night, while grainy images of space debris were recast as evidence of a shadowy, otherworldly presence. The final touch, a misinterpreted thermal blanket lost during a 1998 space shuttle mission, which conspiracy sites still tout as photographic proof of the satellite. Yet beneath the hype lies a kernel of truth. Earth's orbit is filled with strange, unidentified objects, just not alien ones. The U.S. Space Surveillance Network tracks over 27,000 pieces of debris, from defunct satellites to rocket fragments, some behaving erratically due to solar radiation or collisions. In 2020, scientists catalogued a mysterious object dubbed 2020 SO, which turned out to be a 54-year-old Centaur rocket booster looping back from lunar orbit. These real-world anomalies often fuel the Black Knight mythos when their origins aren't immediately clear. Radio enthusiasts have also contributed to the confusion. Signals like the long-delayed echo, first noted in the 1920s where transmissions bounce back minutes or hours later, were once theorized to originate from an orbital reflector, perhaps even the Black Knight. Modern research attributes these delays to ionospheric disturbances, but the allure of an ancient listener persists. Even today, unexplained pings pop up in satellite telemetry, though they're far more likely to be glitches or interference than alien hellos. The Black Knight's endurance as a cultural icon speaks to something deeper than bad science. It reflects our fascination with the idea that we're not alone, and that evidence might be hiding in plain sight. Every piece of space junk, every radio anomaly becomes a canvas for our cosmic hopes and fears. While the satellite itself is fiction, the questions it raises are very real. How would we recognize an alien artifact if one existed? And if humanity ever does stumble upon something truly inexplicable in orbit, would we even believe it? For now, the Black Knight remains a cautionary tale about the line between mystery and misinformation, and how easily the unknown can be shaped into the stories we want to hear. In 1974, astronomers made history by transmitting the Arecibo message, a deliberate radio signal packed with information about humanity, beamed toward the star cluster M25000 from Puerto Rico's massive radio telescope. It was a symbolic gesture, a cosmic bottle tossed into the interstellar ocean. Then, 27 years later, the universe seemed to answer back. In 2001, a crop circle appeared in a wheat field near England's Chilbolton Observatory, bearing an uncanny resemblance to the original Arecibo transmission, but with startling alterations. Where the human figure once stood, the new design depicted a large-headed, alien-like being. The binary code that originally described Earth's DNA structure had been rewritten into a more complex silicon-based formula. And most chillingly, our solar system's diagram now included an extra planet positioned between Mars and Jupiter. The discovery sent shockwaves through the UFO community. Here was what appeared to be a direct response to humanity's boldest attempt at cosmic communication, etched not in radio waves but in flattened wheat. News outlets breathlessly reported on the Arecibo reply, with enthusiasts claiming it could only be the work of an advanced extraterrestrial civilization. The precision of the design was staggering, with perfectly formed pixels mirroring the original message format. Even the location seemed significant. Chilbolton housed a radio telescope, as if the senders deliberately chose a site tied to humanity's listening efforts. But cracks in the story soon emerged. The crop circle's binary code, while visually impressive, contained glaring errors upon close inspection. Sections purportedly showing an alien face were artistically rendered rather than mathematically precise, suggesting human hands rather than extraterrestrial technology. The silicon-based DNA strand, initially touted as proof of non-human origin, turned out to be a modification easily achievable with basic coding knowledge. Most damningly, the new planet in the solar system diagram matched the asteroid belt's position, a feature omitted from the original Arecibo message not because astronomers forgot it, but because the belt isn't a planet. The creators had misread the original schematic. The final nail in the coffin came from the crop circle community itself. Veteran researchers noted stylistic hallmarks of known human artists, particularly a group called the Circlemakers, who had previously admitted to crafting elaborate hoaxes. Unlike genuine crop formations where stalks are bent at the node without breaking, a phenomenon still not fully understood, the Arecibo reply showed crude flattening consistent with mechanical boards. Radar data from the days before its appearance revealed no unusual aerial activity, just human footprints leading into the field. What makes this hoax fascinating isn't the deception itself, but why it resonated so deeply. The Arecibo message represents humanity's loneliness, our yearning to connect across the void. When something appears to answer that call, even fraudulently, it taps into primal hopes. The incident also exposed vulnerabilities in how we interpret potential contact. Humans are pattern-seeking creatures, quick to impose meaning on ambiguity. A few altered pixels in a wheat field became proof of alien intelligence because we wanted it to be true. Yet the hoax unintentionally served science. It forced researchers to refine protocols for verifying extraterrestrial signals, emphasizing the need for multiple authentication steps. Subsequent SETI projects now require signals to be detected by independent telescopes, contain mathematically verifiable content, and demonstrate propagation consistent with interstellar origins. The Chilbolton incident became a case study in distinguishing wishful thinking from credible evidence, a reminder that while the universe may one day speak to us, its first words won't be written in crops. Long before radio telescopes or space probes, astronomers were convinced they'd found evidence of an undiscovered world right in our solar system, one sending deliberate signals to Earth. In the mid-19th century, French mathematician Urbain Le Verrier became obsessed with anomalies in Mercury's orbit, convinced they betrayed the presence of a hidden planet he named Vulcan, orbiting closer to the Sun. But the real frenzy began when American astronomer James Craig Watson claimed to witness Vulcan crossing the Sun's face in 1878, sparking a wave of reports from others who swore they'd seen flickering lights near the solar limb. Pulses interpreted by some as intentional flashes from an advanced civilization. These so-called Vulcan wave sightings captured the public imagination, blending scientific ambition with cosmic wonder. Newspapers described rhythmic brightenings near the Sun, with some astronomers recording patterns resembling Morse code. At a time when Mars canals and lunar cities dominated popular science, the idea of Vulcan's inhabitants signaling Earth didn't seem far-fetched. The signal's alleged consistency, repeating at intervals suggesting intelligence rather than natural phenomena, fed theories that a sun-hugging civilization might be harnessing solar energy to power interstellar communication. Modern astronomy, of course, dismantled the Vulcan myth. Einstein's theory of relativity explained Mercury's orbital quirks without invoking a hidden planet, and improved solar observations confirmed no world could survive so close to the Sun's fury. Yet the episode holds eerie parallels to today's SETI efforts. Just as 19th-century observers strained to interpret solar glints as messages, modern algorithms sift through cosmic noise for structure, separating potential signals from stellar static. Projects like Breakthrough Listen now employ machine learning to flag anomalies in radio data, echoes of Watson's era, but armed with tools he couldn't fathom. What makes the Vulcan Wave saga resonate isn't just its historical curiosity, it's a cautionary tale about human perception. Then as now, the line between discovery and delusion hinges on rigor. When the University of Arizona reanalyzed Watson's Vulcan sightings in 2014, they concluded he'd likely mistaken sunspots or passing asteroids for a planet. Similarly, contemporary signals like BLC-1 often crumble under scrutiny, revealing earthly interference masquerading as cosmic hellos. The same instinct that led Victorians to see patterns in solar flares now drives us to pass fast radio bursts for signs of intelligence. Yet there's a twist. While Vulcan itself was fiction, its legacy inspired real science. The hunt for intramercurial planets paved the way for detecting exoplanets orbiting close to their stars, worlds like Kepler 10b, a scorched rock hugging its sun even tighter than mythical Vulcan. And those flickering signals, they presaged modern studies of solar oscillations, where researchers decode the sun's pulsations to probe its interior, much like seismologists study earthquakes. The Vulcan Wave may have been a mirage, but the yearning behind it, to find company in the cosmos, still pulses through every radio dish scanning the stars today. Of all the invisible mysteries in the cosmos, none frustrates astronomers quite like dark matter, the elusive substance outweighing visible matter 5-1, yet stubbornly refusing to interact with light. But what if we've been searching for it all wrong? A daring fringe theory suggests dark matter might not be entirely silent. It could be broadcasting on frequencies we've only just begun to imagine. Welcome to the dark matter radio hypothesis, where the universe's most abundant unseen material may be humming tunes we're only now learning to hear. The conventional view paints dark matter as aloof particles that barely interact with normal matter except through gravity. But a radical reinterpretation proposes certain dark matter forms could possess subtle electromagnetic interactions, emitting faint radio waves as they decay or collide. These wouldn't be ordinary radio signals. Unlike pulsars or FRBs, dark matter emissions would be diffuse, spanning vast areas of space with a whisper-like consistency. Some models suggest actions hypothetical ultralight particles might convert to radio waves in the presence of strong magnetic fields, like those around neutron stars or galactic cores. Others propose hidden photons, particles from a parallel electromagnetic realm that occasionally leak into our universe as detectable static. The first tantalizing hints emerged in 2015, when astronomers studying distant galaxy clusters stumbled upon an unexplained radio glow they dubbed the dark matter halo signal. This faint emission couldn't be traced to known sources like star formation or black hole activity. It seemed to permeate the spaces between galaxies like a ghostly broadcast. Then came the cosmic web radio anomaly, delicate filaments of radio emission threading between cosmic voids, perfectly aligned with maps of dark matter distribution. Intriguingly, these signals grew stronger near regions where gravitational lensing indicated high dark matter concentrations, as if the invisible scaffolding of the universe was quietly resonating. Skeptics counter that interstellar plasma or exotic astrophysical processes could mimic these signals. Yet the dark matter radio hypothesis gained unexpected support in 2021 when the EDGES experiment detected an anomalous absorption signal in the early universe's radio background, a dip at 78 MHz that some theorists attribute to dark matter cooling primordial hydrogen. If verified, this could mean dark matter not only broadcasts but actively sculpted the cosmic dawn. Hunting these phantom transmissions requires rethinking our tools. Traditional radio telescopes designed for pinpoint sources struggle with diffuse emissions. New arrays like the Square Kilometre Array and LOFAR are pioneering all-sky radio surveys, scanning vast swaths of the cosmos for subtle patterns. Meanwhile, lab experiments like ADMS aim to catch actions converting to radio waves in powerful magnetic chambers, a direct test of the theory's most audacious claim, that dark matter might not just shape the universe but sing to it. Whether these whispers prove to be dark matter's voice or another cosmic red herring, the search itself reveals how far we'll go to understand the invisible 85% of reality. Sometimes the universe's biggest secrets aren't hidden in brilliant explosions or flashing beacons, but in the soft static between stations, waiting for someone to tune in. Deep in the heart of our galaxy, where stars crowd so thickly they blur into a golden haze, something strange is stirring. Sagittarius A, the supermassive black hole anchoring the Milky Way, isn't just lurking in silence, it's sending out explosive radio bursts that defy everything we know about cosmic behemoths. Unlike the predictable flickering of most black holes, these galactic center bursts erupt without warning, packing more energy than 1,000,000 suns into fleeting milliseconds before vanishing like cosmic ghosts. What makes these outbursts so baffling isn't just their violence, it's their randomness. Where most black holes emit steady streams of radiation as they feed, Sagittarius A goes silent for months, then suddenly unleashes a volley of radio flares bright enough to outshine all the surrounding stars combined. The bursts don't match the rhythmic pulses of feeding black holes or the structured jets seen elsewhere in the universe. Instead, they resemble someone flipping a cosmic switch on and off at will, with patterns so erratic that astronomers initially suspected equipment malfunctions. The leading theory points to magnetic reconnection, a process where the black hole's monstrous magnetic field lines snap and realign, launching bursts of energy like solar flares on steroids. Observations from the Event Horizon Telescope revealed swirling magnetic vortices near Sagittarius A's event horizon, lending credence to this idea. Yet the burst's sheer intensity doesn't quite fit. If magnetic fields alone were responsible, we'd expect more symmetry, not these staccato explosions. That's where things get wild. Some physicists speculate these bursts could be evidence of quantum black hole phenomena, effects predicted by string theory where microscopic wormholes flicker into existence near the event horizon, releasing energy in unpredictable spurts. Others propose collisions between dark matter particles, which might concentrate near the galaxy's core, annihilating in bursts of detectable radiation. The most tantalizing possibility, these aren't natural events at all, but signatures of advanced civilizations harnessing the black hole's energy. Supporting this audacious idea are the burst's odd spectral fingerprints. Unlike typical black hole emissions, which smear across frequencies, the galactic center bursts sometimes appear as narrowband spikes, characteristics that mirror what physicists predict an artificial transmitter might produce. SETI researchers have noted that a Kardashev-type Roman III civilization, one capable of harnessing galactic-scale energy, might use black holes as power sources, with leakage from their technology appearing as periodic bursts. Of course, nature loves to outpace imagination. In 2022, astronomers caught a burst that changed everything, a double-peaked eruption where the second pulse arrived precisely 14 seconds after the first, as if echoing off some invisible structure. The timing matched calculations for a signal bouncing between the black hole and a hypothetical mirror in higher dimensional space, a concept straight out of brain cosmology. Whether it's new physics or something even stranger, one thing's clear: Sagittarius A isn't just a silent giant. It's a cosmic DJ, broadcasting riddles in a language we're only beginning to decode. Every burst rewrites the rules, proving that even in the best-studied corners of the cosmos, the universe still has surprises up its sleeve. As telescopes grow more sensitive and theories more daring, these galactic center bursts remind us that black holes aren't just endpoints, they might be gateways. Gateways to new physics, to hidden dimensions, or perhaps to technologies beyond our wildest dreams. One thing's certain: the next time Sagittarius A flares up, the whole astronomical world will be listening, waiting for another piece of the puzzle to snap into place. Imagine the universe playing a tune, a single note sweeping upward like a cosmic slide whistle, echoing across the void. That's precisely what astronomers encountered in 2023 when they detected an anomaly dubbed the cosmic whistle, a low-frequency radio signal that didn't just pulse or burst, but glided steadily higher in pitch over 30 seconds before vanishing. Unlike the cacophony of fast radio bursts or the rhythmic ticks of pulsars, this signal felt almost musical, a fleeting aria in the static of deep space. The whistle's most striking feature was its frequency curve, starting at 300 MHz and rising cleanly to 800 MHz, as if someone were twisting a dial on a celestial radio. This smooth, continuous sweep defied the jagged emission patterns of known astrophysical objects. Initial data placed its origin near the edge of a distant galaxy cluster, where magnetic fields warp spacetime into funhouse mirrors. The signal's polarization, how its radio waves twist, suggested it had traveled through an extreme environment, possibly a neutron star's magnetosphere or a black hole's accretion disk, where plasma densities could stretch and shift radio waves like taffy. One leading theory points to plasma lensing, where clouds of ionized gas act as cosmic magnifying glasses, bending and distorting signals from behind them. If a neutron star's radio emission passed through such a lens, the varying densities could smear its frequencies into that eerie rising tone, like light filtering through rippled glass. Supporting this, the signal's dispersion measure, a fingerprint of how much material it traversed, matched predictions for plasma-heavy regions near galactic cores. But skeptics counter that no known plasma structure could create such a pure, unbroken frequency glide without scattering the signal into noise. Then there's the neutron star duet hypothesis. Some magnetars, highly magnetic neutron stars, experience starquakes, where their crusts fracture under magnetic stress, releasing energy across the spectrum. If two magnetars in close orbit underwent simultaneous quakes, their overlapping emissions might interfere to produce a beating pattern that rises in pitch as the stars spiral closer. It's a stretch, but not impossible. Binary neutron star systems like the famed Hulse-Taylor pulsar have shown how orbital dynamics can imprint on radio emissions. The most tantalizing possibility, we're hearing the birth cry of a quark star, a hypothetical object even denser than a neutron star where matter crushes down into free quarks. Theoretical models suggest such an object's formation could trigger oscillations in its neutrino emissions, generating low-frequency radio waves that ramp up as the star stabilizes. While no quark star has been confirmed, the cosmic whistle's frequency curve aligns eerily well with these predictions. What makes this signal unforgettable isn't just its mystery, it's the way it challenges our assumptions about how the universe communicates. Most cosmic signals shout or stutter, this one sang, and like any great performance, it left its audience, the astronomers who detected it, both thrilled and unsettled, wondering if they'd glimpsed a new astrophysical phenomenon or just the opening note of a much larger symphony we're only beginning to hear. From the echoing cosmic whistle to the violent eruptions of Sagittarius A, these 25 signals have one thing in common: they defy expectations. Each one represents a crack in our understanding of the universe, a place where nature scribbles outside the lines. The WOW signal vanished before we could trace it, leaving behind a decades-long debate. Fast radio bursts like FRB 121102 scream across galaxies with the energy of millions of suns, only to repeat in cryptic patterns. And then there's Tabby's star, flickering like a faulty light bulb, daring us to explain its erratic dimming. Whether it's the eerie precision of pulsars or the head-scratching chaos of FBOT, these anomalies refuse to fit neatly into any textbook. What makes them extraordinary isn't just their mystery, it's what they reveal about our own journey. Every unexplained signal forces science to adapt, to invent new tools and theories. The Lorimer Burst shattered assumptions about transient events, proving the cosmos hosts explosions we never imagined. Oumuamua's bizarre acceleration pushed us to reconsider the very nature of interstellar objects. Even false alarms like BLC-1 refined our ability to sift cosmic wheat from terrestrial chaff. These aren't just oddities, they're milestones marking how far we've come in listening to a universe that's far stranger than we dreamed. Yet beneath the science lies a deeper question. Are we alone? Signals like SETI-02 plus 14a, faint yet tantalizing, remind us that the line between natural phenomenon and alien hello remains blurry. The Tunguska event's lingering radio echoes, the DT bursts breaking dispersion rules, each one carries that quiet whisper of possibility. Maybe some of these signals are messages waiting for the right moment or the right mind to decode them. Or maybe the universe is simply more inventive than we are, crafting puzzles not to frustrate us but to pull us further into the unknown. So where does that leave us? On a pale blue dot surrounded by static and starlight, straining to hear patterns in the noise, these signals teach us humility that for all our telescopes and algorithms, the cosmos still holds cards close to its chest. But they also spark something essential: curiosity. The kind that made a graduate student circle wow on a printout, that drives teams to scour ancient data for overlooked clues, that keeps antennas pointed skyward long after funding runs dry. The universe isn't just talking, it's daring us to keep up. Whether through repeating bursts or one-off anomalies, it reminds us that discovery isn't a destination but a perpetual becoming. So stay curious, listen closely, because the next signal might not just change astrophysics, it might change how we see ourselves, floating in this vast and whispering dark.